some organic materials. I still don't know, sort of like the last speaker, if I fit in this session, but I couldn't make the first week where I probably would have fit better, so they very kindly shoved me in here. But at least I'll have organic materials running around, so maybe that is close to the topic for this week. The neat thing I'm going to try to tell you about is a class of materials that are really easy to work with, and by easy to work with, I mean a bunch of electrical engineers like myself go into a chem lab and mix these up and can do good stuff. If you get interested in these, I'd still recommend having a real chemist work with you. But they are fun and they're easy to work with, and so I'm going to hopefully give you enough background that if they fit some application you've got, then you can play with them. So for lectures, I warn you, I am an engineer, so for the physicists in the crowd, I'm sorry. I can't go more than about 20 minutes without talking about applications. So I will. And I don't need to read that because you can read. Okay, that was just abstract. I just like to include them in my talks and what they're doing. So I'm going to start out with just the real basics on what these things do and how they do it. I'll warn you, I am an electrical engineer talking chemistry, so if there's real chemical physicists or chemical engineers out there, please plug your ears and come back in a couple of lectures and I'll review. People familiar with photopolymers materials? I thought I would motivate this. I'm getting nothing. So okay, if you're not familiar with photopolymers materials, you're going to get two for the price of one. I thought I would motivate these photopolymers by comparing them with photorefractives. So if you don't know photorefractives, then you'll get two for one. Photorefractives, like lithium niobate that was just mentioned in the last talk, are typically grown crystals, and you slice chunks of those boules out. These materials I'm going to talk about, you go in your kitchen and you mix them up, and then you typically cast them perhaps between glass slides. And already you can see beginnings of why you might like this in terms of applications. So let's walk through how a photorefractive works, and then if you know this already, you can go to sleep, and then I'll do the comparable material on the left. You might bring in one of those slabs of photofractive material, two coherent plane waves, and they would create a standing wave, and that standing wave is some sinusoidal intensity distribution versus space. You have some donor atoms in lithium niobate, it's typically iron, and the light will excite some electrons up in the conduction band, so we now have some separation of the charges on an atomic scale. If you look right away, immediately after you apply that light, you find, and you look at the charge density, coulombs per meter cubed, you find that you have a positive charge distribution, which looks like a copy of the optical intensity, and then you have a negative charge distribution, the electrons, which is the mirror image of that, and you sum those two up, and you get nothing. But the donors are atoms that are in the matrix of the crystal, and they don't move. The conduction band electrons, of course, are in the conduction band, so they can move, and these are therefore free to diffuse. And so, if all else being perfect in a long time, the electrons will diffuse out to be completely uniform, and we now get a charge density that we can see, which is we've simply revealed the positive charge density of these ionized donors. And it still looks like a copy of the intensity. And then because we have charge separation, we get a space charge, generates an electric field, and the electric field, through the electro-optic effect, makes an index of refraction. So photorefractives, by the way, are a lot of fun because there's just so darn much physics in them. But the basic processes are not too bad. Notice the index here is 90 degrees shifted from the intensity in this diffusion model. We won't see that in photopolymers. So, if you've never seen photofractives before, there's 30 seconds worth of photofractives. Very, very similar processes now happen in these organic materials. And in a minute, I have some show and tells because I'm also an engineer, so I like to put my fingers on those. I'll show you what they look like. We'll start out the same way. We'll make a standing wave, let's say. And we're going to replace this with all sorts of optical excitations, but we'll start out with a sinusoid. Now what happens? Well, what we've got here in this material, and I'll be introducing the pieces of the materials we go along, but we have a photosensitizer, often a dye. This is exactly like a dye you might have in a kid's toy, a plastic toy. If you ever left a plastic toy out in the sunlight for the summer, particularly if it's a red toy, so it absorbs blue light, it gets less red over the course of the summer, right? As the photons go in and they break the dye molecules into radicals, and those radicals then tend to attack the plastic of the toy. So if you leave a red toy in the sunlight over the summer, it tends to fall apart in your hand towards the end of the summer. We're going to use exactly the same processes here. The dye is going to absorb some photons, and what running around in this material will also have monomers. From the Greek, mono is one part. These are small molecules. And the excited dye, that's excited because it got hit by a photon, will cause them to join up into polymer, from the Greek, many parts. And so we will locally create polymer, and locally, where we have bright lights, reduce the concentration of monomer. Notice that it's cleverly even color-coded to look like what we got on the left here. All right. So now we've made some material. If we look at the mass density, not charge density, immediately after that optical excitation, we see polymer that looks like a copy of the optical intensity, and we see monomer, which looks like some mirror image of that. And so you sum those two up in the absence of shrinkage or other nasty organic effects, and the mass density will look completely uniform. However, as you let time go forward, these are big molecules. They don't diffuse very fast. As a matter of fact, after they're more than 2 or 3 or 4 monomer units hooked together, they pretty much are completely stationary. We're going to use these organic materials above what's called their glass transition temperature. If you take most polymers and you heat them up enough, they will go from a glassy state, like this stuff, to something rubbery. And when it's rubbery, then small molecules are able to diffuse through it. And that's why we tend not to operate them in that state, because we don't want stuff to diffuse into them if you made a computer or something out of it. So the monomers are able to diffuse. And so in the long time limit, they are going to diffuse to be completely uniform. So now, because the monomer is uniform, now I reveal the distribution of polymer, which looks like a copy of the optical intensity, and that translates directly into a change in the optical index of refraction. Much simpler physics than in the case of the photofractives, where we have to go through an electro-optic effect. So, I'm going to go through this a couple of different ways to make sure you got it. But the basic idea is it's a very, very simple system that has this neat property that I can put any optical distribution in 2 or 3 distributions onto one of these materials. Some chemistry happens here, some diffusion happens here, and I get a copy of my optical distribution showing up as an index distribution. And that's kind of magic. You can make lots of cool widgets out of that. I'm an engineer, so I like widgets. So let me, a quick comparison, just in case you are familiar with these materials. We routinely get dealt in up to 10 to the minus 2. You can go beyond this, but you start paying for it in shrinkage. You're taking molecules that are floating around in space and you're joining them up, and of course that's moving them together. And as you move them together, that corresponds to the bulk shrinkage. A lot of good chemical engineering has happened to bring this number down to a point you don't care. As you make more and larger delta N, which generally means you're doing more chemistry, you tend to get more shrinkage. This is a really neat thing. Now, getting up to the infrared takes a sort of bold chemist, but one can sensitize these materials all the way up into the infrared. And that's tough because these are pretty low energy photons for doing chemistry with. Typically, you think blue to near UV is where you do photochemistry. This is a good thing if you're an engineer. Generally, you work on them once and then you're done. If you want to make widgets, that's okay. A lot of these materials were used for interesting optical processing sort of applications, where you do dynamic holography and do really cool computing kind of applications. These aren't quite so good at that. You can do some clever chemistry and break bonds back apart with deep UV and run backwards. I want to make widgets, so I don't care. Generally organic, you can put inorganic components in the chemistry. And here, these things have been very, very well described, and you can go and calculate what's going to happen. Here, not so much, and the reason is basically this fun, good and bad of organic chemistry, and I'm going to try to convince you that it's fun and you should play with it, is that you can go in and change it very easily. You can add new functions and modify what happens and switch in different materials and get all sorts of different properties, and that keeps your theorists from ever catching up with you. So you end up having to sort of do your own theory because there's just such flexibility in the materials. So let me give you a cartoon view now of how we'll use that. And then I'll show you actually some parts. I've got some here, I'll show it to you. Let's say I get a slab of this material. Little blue M&Ms are monomer, and little orange M&Ms are my initiator, my dye. And I'll bring some light of any type and variety, but I'll show you this one in an example, on the material that excites these photoinitiators. In the case of radicals, which is the most common element, it breaks the dye in two, and I get one or two radicals out of that. And that then starts a process. Oh, very important. The light goes away, and very little has happened here yet. Certainly some chemistry may have been started, but very little diffusion has yet started. And I'll show you, as my graduate students would say, in the case that they ever want to graduate, why this is a good thing. It massively simplifies your understanding of materials. So diffusion starts to happen with clever PowerPoint magic, and you start building these polymer chains, and you get a density of chains that's very high where you're exposed. Once you're done, and you can do this one time, or in the case of data storage, you can do it on the order of 1 trillion times. You then want to get rid of any remaining photosensitivity. If you're making widgets that you let out of the real world and they're still sensitive to room lights and things, that would be a bad thing. So you bring in a big uniform cure, big optical intensity, or it could be heat perhaps, that excites the remainder of the dye in the material. That causes polymerization to happen everywhere. The dye typically bleaches, just like that kid's toy left in the sunlight that gets less red. So I get high optical clarity. But I get a higher density of chains where I exposed, because diffusion happened, and so I end up with a copy of my light as an optical index distribution. So that's the same thing I just said before, but now more of a PowerPoint cartoon version. Any more? All right. Okay, I'm going to stop and do something weird for a minute. And I'll start passing show and tells around. What I'm going to talk about a lot is how you do a sort of physiochemical modeling of these systems in order to motivate design and get new materials and do new things. You can pattern deeply in 3D, you can pattern down at the nanometer scale. And you can't say anything about modeling something unless you have some way of measuring what you model. So this may seem like an aside, but I'm going to talk about 3 or 4 different ways, at least mention different ways, that you can reach down and measure this thing you just made. Because if you can't measure it, then you can't model it. I'm putting myself a little timer here, but my iPhone seems to want to turn off. So this is one of the systems that we've developed to model or especially these materials. And also in the next slide, I'll show you some pictures of the real things that I'm talking about. For any of you that are sort of optics jockeys, you may be familiar with the idea of, in a microscope, it has a certain transfer function. There's certain spatial frequencies it can see within the material. And you have to be very clever and careful on the design of microscopic measurement systems when you're measuring these kind of devices, because what you really want to do is a quantitative microscope. Biologists typically don't want quantitative microscopes, they want good pictures. And they may want resolution enhancement, or it shows them what they want to see, but they don't really measure things most of the time. We want to measure something here. We want to measure the index of refraction. So that takes a lot of thought on how you get what you get that. In this case, we have one of these sandwiches. This is glass, polymer, and glass. And we made some sort of structure down in this polymer. And what we'd like to do is we'd like to bounce some light off of it. It's characterized with lenses right there. And measure the Parnell reflectivity change between the glass, which is pretty uniform index, because people want to make glass, and the variable index of refraction that might be on this surface that we made in polymer. And then we can invert the Parnell reflection coefficient, and we can find what the index change was. The problem with that is if you bounce some light off that surface, you're also bouncing it off that surface, and you're also bouncing it off the back surface, you're bouncing it off everything. And these reflections are actually much, much greater than the tiny little reflection at the interior boundary there, and you can't separate them out. So you can use what's known as optical frequency domain reflectometry, which if you know, then you understand. And if you don't know, it's the frequency domain version of optical time domain reflectometry. And so you can think about replacing this with a pulse laser in time domain. And I send a pulse in here, and I take the pulse back out, and I can now see the different surfaces because the pulses show up at different places in time. This is a system where you do that with a tunable laser. You get a set of interference fringes that occur over here, and then before you transform those, and you get pulses that show up in time, and there's the front air glass boundary. Here's the boundary I want to measure on the inside. Here's the back boundary out here. This actually is much, much weaker than these two, but I have also some focal filtering going on, if you know what a focal microscope is. The point is, if you build an instrument, you're kind of careful with calibrating it. These systems have really high signal-to-noise ratio, up in the 130 dB range, which is nice when you want to measure small changes. You now get a microscope which can precisely measure index refraction on the micron scale. To check that out, you look at a gradient index fiber. There's the boundaries of the fiber, there's the cladding of the fiber, there's the parabolic core of the fiber. The manufacturer tells you it's 2% index contrast, and by color, that's the same thing you measured. You can see that their diffusion process wasn't quite complete, and it's not quite parabolic. Why do you care? Because now you can go off and measure these materials and make really good pictures as well. Let's do some modeling. Let's take a slab of this material. It's about 1 millimeter thick between 2 glass slides. In fact, I'll hand out. Maybe I'll just hand around my show and tells. I'd like to get these back at some point, so, but they're relatively damage tolerant. And there's some waveguide arrays there, some lenslet arrays, and you're doing exactly the right thing. You need to look up near the light and you'll catch the interior refraction, because they're all fitted structures. Let's bring 2 beams of green light, maybe 5 millimeters in diameter, onto this millimeter thick slab of material. That will, of course, record a hologram, fix the material, and we can come back in now with that scanning microscope, and we can actually see the gradients that we've made. Here's the material we didn't expose. That's the index change of 0. The index goes low in the dark fringes because diffusion pulled mirrored material out of the dark fringes, and it piled monomer up in the bright fringes of the hologram. Because these are Gaussian beams, our intensity was going up this way, so we get sort of a series of exposures, and we can use that to fit some material model that would tell us if we understand how this is developing. To my knowledge, this is the first such picture that's ever been made. What people typically do to model these things, folks like John Sheridan at College Dublin, is they send in 2 beams, make a hologram, and then with a red laser, they diffract off of that hologram, and then they can measure the first order Bragg scattering, which I personally find less than exciting or less than convincing, because what we really care about in modeling these things is the response that wasn't linear. And so the parts of this structure which are not copies of the intensity, and those are the parts you can't see with Bragg scattering. So this is kind of cool, because we can now actually measure the actual index refraction locally, and we can go and extract what's the shape of all those curves as a function of moving our way up here. And they're weak at the edge, and they get stronger in the middle, but not strong enough, only something is saturated. And these are sort of, but not completely sinusoidal, and in that information is the beginnings of understanding how the material is really responding. The story I told you previously was obviously the sort of kid bedtime story of how they work, and the devil is in the details. And one of those samples, the kind of glass slab-looking one, we can then do this with. I said I had to talk applications, so here it is. World's simplest thing you can do. Just step and repeat your way along. Notice that every time in PowerPoint land, I hit the material with light, and then diffusion takes over and an index shows up. And that is really nice to not have extraordinarily complex optical nonlinear propagation problem. And so that's a phase microscope picture of the part you've got floating around, or probably similar, but not exactly the same one. And I can just step and repeat my way across here. This looks like bumps in rubber sheet, but that's what the IC photographs look like. This is actually a millimeter thick slab of material, no surface features, and this is just showing us the phase features. Yet another quantitative index measurement system we worked on in my lab that works nice in transmission can go actually measure the precise index profile of these guides, or lenses. Delta N of around 2 times 10⁻³ and then you can go look at individual lenses, and you can fit a parabola to it, and by quality it is a parabola, so it's a pretty high quality lens. You see little dips at the edges, that's diffusion happening again. So where did this material come from? Well, it came from everywhere else. And so if you don't wait forever, and you get tired and want to graduate someday, so you get cured the material, you've left a little dip there where the monomer was still working its way in. But you get up to kind of reasonable delta n's. And of course, you can just program this thing up and make it whatever you want. And I think that's the interesting thing. Okay, so that's the sort of cartoon introduction. You're not rate limiting me. You're lost. I'm having fun. Okay. Let's talk about the fun physics. So again, I'm an engineer. What I want to do is I want to figure out how to model these things, not just because I like to model, because I want to go in and figure out how I can manipulate the different bits of the physics to make devices that I couldn't make before. So I want to write down the physics and understand how I can get some understanding out of it. So we've got 3 bits of physics. We've got obviously optical diffraction happening here, particularly we're in deeply 3D. There's one of those samples that's a centimeter thick. So we gotta worry about diffraction. And that's Maxwell's equations, check. Then we've got reaction. That's the chemistry happening. And that's written as a series of rate equations. They always look like first derivative at time of something is changing because of other stuff. And there might be optical intensity in here, and then density of various chemicals. And you can make this as complex as you'd like. There's a whole series of inorganic materials, a lot of different species that are running around. And the trick is to make it as simple as possible and still keep the physics that are important. And then the important part is finally that we have diffusion. Because if diffusion wasn't happening, then none of this would be interesting at all. Because that's what's moving stuff around and making the permanent index change. An example of where, let's walk through the coupler. Why this is now, maybe it's not so 3 equations. It's not so bad. Yeah, they're differential equations, but what's the big deal? Well, the optical field shows up in driving the chemical rate equations through the intensity. Then, as we begin to eat up some species or create some species locally in space, little square brackets here mean density. So these are the densities of various chemicals, and I'll define these terms here in a minute. As we begin to make something or remove something, then diffusion takes over. Well, it still doesn't look too bad. It's just series. It goes top to bottom. I can do that. But of course, it also goes backwards. So as we begin to move species around, that then locally changes the chemistry and changes the index of refraction of the material. And so it's a coupled nonlinear partial differential. Every bad word there is. I mean, it's just a nasty set of equations. If I made it to Sydney, it would have been fun to show this to Martin Stark. He would have recognized it. An example of the sort of full-on nastiness that would involve all these things is to focus a beam or poke a fiber or something into some sensitive material down here, beam's propagating up, and just let the light go on up. And what happens then is you begin to expose some material, begin to cause polymer to develop, you begin to move monomer in, the density begins to go up, the index of refraction goes up. I just walked down through these equations. And I begin to get some self-focusing, and the light, which is still on, this will sort of narrow, won't diffract so much. And you can get this idea in your head, as many people have, that I could sort of have a waveguide that would write itself out across this material in a vaguely soliton-like fashion. And that would be cool. It would be perfectly aligned to whatever the source is down there. And it's incredibly hard to make that happen. And it's because these are not the world's most predictable set of equations. And so what tends to happen is you have too little light and it just diffracts out, or you have too much light and it self-focuses, or more likely you have some tiny little scatter here, and that scatter builds up and the thing starts to filament. You can see this going on here. And it's just a really hard problem. Martin, as a theorist, spent a fair amount of time, so probably 2 or 3 graduate students, trying to get a theoretical handle on this. It's really hard. So in general, I'll avoid this by having this happen first, and then I won't have to worry about these 2 things being coupled, because they will take over second. So why is this hard? We don't really know what all these equations are. If you go work with your chemists, that's the fun of organic chemistry, is there's all these side reactions and they're really sure what's going on. Even if they do know what all the rate equations are, they don't know all these constants. And there's ways to measure them. Laser flash photolysis and time resolved spectroscopy, but those are not trivial experiments. Also, if you've never worked with chemists, you need to understand the jargon. These are called constants of the reaction. And constant in chemical jargon means thing that changes. And then they do. Because, for example, this is saying right here, I've got 2 different species somehow interacting, and that causes something to happen. And there's some proportionality constant there. Well, as the matrix gets hard, because I'm doing all this cross-linking, or as one of these molecules starts to get big, because it's a polymer and I'm building the chain, diffusion coefficients drop. They can't move so much. If they can't move so much, they don't react so much. And so a lot of these constants actually do change as the reaction progresses. So I'm going to duck all that, because I'm an engineer, and I want to go out and make things, and we'll work in the early parts of the reaction where they do tend to be constant. But then, even if I know all those things, I want to get some analytic solutions out of this so I can go off and make predictions and make good stuff happen. So, I'm going to walk you through a little bit of chemistry. If there's real chemists in the audience, please don't hurt me. To give you, again, an idea of what's the important physics. And we'll keep coming back to these. These are almost enough to describe almost anything you want to do, and that's cool. So, we got something called this photoinitiator. That's the dye in the kid's toy. It interacts with some intensity, that's the I, and that is going to turn out to create excited photoinitiator. That's breaking the dye in two and making my radicals very active molecules like they go off into chemistry. And maybe it diffuses, because dye is a small molecule, so it's a fixed long term. The active photoinitiator, dot, is the chemistry notation for a radical, so that's the active photoinitiator. Gets created in the same way this guy is getting destroyed. And there might be some explicit terminator in this material. There's two reasons it might be there. One is you want to ship this material to your friend in Australia, and you don't want it to get thermally excited by being in a hot airplane. If there's photons have enough energy to break these bonds and cause stuff to happen, then thermal excitation can do the same thing. So you might put a terminator in there just to kind of keep the whole reaction shut down from little bits of excited photoinitiator get created. The other real thing is oxygen turns out to be an extremely efficient terminator of these radicals, and unless your graduate students are really good at holding their breath, there tends to be a lot of oxygen in your materials, and so you sort of have to deal with the fact that there may be a species in there that shuts the reaction down. So here we see just a negative sign in this equation, that we have this thing trying to get created by the optical intensity, and then there's some species which is eating them back up. And what typically happens is it eats up these radicals, stops the reaction until it's gone, until you use it up. And the reaction proceeds as normal. And that turns out to be really, really cool. And that's about half the talk, is talking about why that's something we could exploit. Okay, so now you got to write an equation for the terminator, and it's this term says the terminator is disappearing because it's eating photoinitiator, and photoinitiator is disappearing because it's getting terminated, and the terminator is disappearing. They're bonding and making some molecules which will now more. Oxygen's small, so they're dealing with it, they're diffusing. So that's all the initiation kinetics. We've got three different species: the dye, the excited version of the dye, and something which is trying to terminate or inhibit the reaction. Then we have monomer. Monomer is getting eaten up by interacting with this excited dye. It better diffuse, because that's what's making all these materials interesting. And polymer is the opposite of that. It gets created with a conversation. And in reality, you should have 15 more equations, but that's enough to get the physics. So, 5 species. Not so bad. Let's see if we can get something analytic out of this. We'll take that equation for those excited radicals getting generated, and let's guess that maybe during the exposure we're in some sort of steady state. And that turns out to be a pretty good guess most of the time. And so it says that the optical intensity, which is trying to create the species, is being balanced by the terminator eating them back up. And that would at least allow us to do something analytic and learn something. So now we can solve for the distribution of these excited things, because that's going to clearly tell us how the rest of the reaction goes. They're driving the whole reaction. And it's proportional to optical intensity. Oh, like I said, and it's a lie, but I'll fix the lie later on. Like I said, we're going to start making copies of the shape of the optical intensity, and here's the first example of that, assuming that these other species are uniform in space and time, which we'll break that soon. But they better be uniform, and if they are, then it's good. And then we can substitute that into the equation for polymer building up, because that's going to make my index of refraction. So just shove that into that really simple equation. And I find that the polymer building up looks just like the intensity if all of these species are constant in time. So it is possible. It's typically done for very weak exposures, where all these materials are very uniform in time. It is possible to make copies of the intensity into the polymer and then the index. And I'll talk about holographic data storage, if you've heard of that. It's either about to be a huge success or finally die its last death in the next year or two. These materials are saying actually were made by a very, very successful company commercializing holographic data storage. And they work in this regime where these are all uniform, so intensity turns into index. I'm interested in doing other things like waveguides that you see in those. And so I really want to make strong exposures and fast, and things that tend to break the small signal limit. And so let's look at this. So here's my equation for polymer building up because there's some monomer interacting with radicals. Let's just take a guess, and this is what I just solved for a minute ago, of now how optical intensity might be building that up. And it relates to these other species. I haven't solved the equations, but let's just take a guess. Let's see what might happen. Let's do a sinusoidal intensity pattern. Here's just one bump in sinusoid. People tend to model these materials with sinusoids because they care about holography. That's what the materials are sort of most famous for, is doing holography. So let's say that's my intensity. And let's just guess that maybe somehow I've eaten up a lot of monomer where I had a bright light. And so I'm not even solving this, I will here in a minute, but I'm just going to guess just to see what happens. If the monomer gets a whole carbon in it, because I'm eating it up where I have lots of light. And what happens is if I multiply this by this, it says right here I multiply, and I find out what the polymer looks like, I see that I might start to develop a dip in my polymer distribution. And what I really don't like as an engineer is the polymer distribution starting to look broader than my light. And I like tiny things, because I'm an optical engineer. And so processes that tend to make my features broader, I don't like. And absolutely every one of the processes you can think of in this material, say one, tends to make the features broader. So that's bad. And here's the one. What if this species, this terminator, that we diffuse oxygen, let's say, what if it gets narrow? Why would it do that? Well, I have the sinusoidal intensity, it's creating radicals, those guys right there, the radicals are reacting with the terminator, and that eats up the terminator. So I start to lose terminator, right, when I have a bright fringe, and this is what's slowing the reaction down. So now it can go faster, right on center. Or if you'd like, it's getting inhibited, it's getting shut off at the edges, and so I get a feature that's narrow. And as an engineer, I look at that and go, ooh, that's interesting. I want to look more at that chemical. And that's actually what basically all my group does now, is play with those kind of species. Because that's good thing. Okay. I'm going to go through this a little bit fast, because I'm getting no questions and no one's able to me, so that means you're all asleep. I'll do one of them, and then they're all listening. It turns out you can solve these equations, at least in a couple of simple approximations. You say, look, I've got a sinusoidal intensity, because people care about holograms, these sinusoids. And if you think, gosh, I've got a cosine came around here, it sort of suggests that maybe you should do a harmonic expansion of all the equations and throw away all the higher order terms just to figure out what the lowest order terms look like, because that's what cosines are good for. So you do a harmonic expansion of all of your chemical species, and you just shove that into the equations, and you solve for what's the interesting stuff going on. This is the first harmonic of that monomer distribution. It's telling me how big this hole is in my monomer. And maybe I'll find that dip in the monomer relative to how much monomer I originally had, the DC. But the interesting thing is this term right here. And let me just talk about that one. This turns out to be something kind of important, and it tells you, if you took nothing away from this talk, how to understand what limits organic reactions. This term right here, which I extracted from the equation, is the diffusion coefficient times something which has got 1 over spatial scale squared in it, and that means it's got units of 1 over time, if you remember your Fick's law. This is the rate of diffusion. The bottom is the polymerization coefficient, one of these constants, times the amount of radical I have. Well, that is the rate of polymerization. So I have the rate of monomer diffusing over the rate of monomer being eaten up. This is a unitless constant, and it tells you whether you're diffusion limited or reaction limited, if you heard those words. If this number is really high, that means diffusion is really fast. I try to carve a hole in the monomer, but stuff monomer diffuses in so quickly that it's like trying to make a hole in water by taking a spoon and pulling some water. It comes right back in, right? So I lower the bathtub of the monomer, go right down, but I never develop a hole because diffusion's fast. On the other hand, if this number is very small, that means diffusion is really slow relative to how fast I'm beating this stuff up. I carve a hole in the honey with my spoon, and the hole hangs around for a while. So this unitless constant tells you whether you're in a regime whether you're going to develop these holes or not. And I can do that without actually knowing any of these constants, which is good, because the experiments to get all of them are sort of tricky. And it turns out the same math happens for every species in here. There's just some new coefficient, which depends on the terminator, the diffusion and consumption rates of those species. Okay, why would I care? I'm just about to end, and I think we'll have time for the questions. Yeah. What we get out of that is a model which we can use to understand what these materials might do. And that's before we've gone off and done the hard chemistry to measure a lot of these parameters. We've got these coefficients R, these unitless things, which are the ratio of a diffusion rate to a consumption or a reaction rate. Let's say I hand you some of that material, which is wandering around, and it's been optimized for doing holography. Maybe these are very, very fine scale things, like you have holography, sub-micron in scale, and it works well there. So I don't know what this parameter is, but I know that I get, I'm going to go backwards, I get good quality recording when I keep all my species uniform, and that means diffusion is fast in comparison to consuming materials. That means this number must be high. That's the message. And now you decide, I want to make something that's 20 times bigger, because that's your particular application. So you have some big scale there. There's little L for little scale, big L for big scale. If you keep all your intensities and all and other factors the same, because you have the same laser that the other guy did, this coefficient, this number which tells you which regime you're in or not, is going to drop like the spatial scale squared. Why? Because that's how diffusion works. It goes to the spatial scale squared. And so if it worked here, it might not work there, because this number drops. And I'll show you, here's the example of that. Let's say you're doing holography. That's what these materials are good for. Going back to my original example. So here's sort of the kindergarten version for holography is that I've got a reference and an object electric fields, and I take the absolute magnitude that squared to get intensity, and presumably that intensity then eventually is going to copy itself into the index for refraction. And we, of course, care about these terms, which are the interference terms. And we tend to not think about these terms, because that's just the intensity of the beams and pairs. So let's see what happens. Well, here's back to the very beginning slide. Here's optical. I just copied the graphics. Here's my optical intensity, and I've got some Sonny set a pattern out of this with presumably less than micron scale. It'd be pretty easy to get down to less than 200 nanometers, as a matter of fact. And if this material works well, that is, I'm going to get a good copy of this into my index of refraction, it must mean that my monomer diffuses quickly in comparison to it getting consumed. And so this number that I'm giving you, this R, must be much, much bigger than 1. Diffusion must be fast. Yay, the material works. Life is good. And I get a hologram. What happens over here? Because you know what? You can't do this. You can't do this without also doing that. These are big, let's say, Gaussian beams or something. So here's some big Gaussian, which is the profile of my beam. It's big. There's 3 orders of magnitude, at least, between those. And so that squared is 6 orders of magnitude. So if this number was big before, it is now small. Or going back to the fundamental physics, my monomer is going to diffuse a hell of a lot slower over a millimeter scale than it will over a micron scale, like a vector a millimeter slower. So what happens now? Something ugly. There's photons here. They're exciting material. The material, the monomer starts to diffuse in, but it's going really slow, and it ends up getting polymerized on the edges and never gets to the middle. And so what you find is you get this ring around your holograms. And that might have been obvious. That's the reason for going through this kind of analysis. So if you're doing holographic data storage, where you want to put order a trillion these holograms in one spot, that might not be such a happy thing. Because you have big optical aberrations here that will absolutely destroy any sort of high-quality optics you want to go through. You can get around that, but it takes more Oh, I think we're doing good. So I think the caffeine is just too much caffeine. Chemistry. Done by electrical engineering. That's lecture 2. What happened? Lecture 5. Okay. All right. So this is a little bit of an advertisement for why you should stay away from the next lecture. And too many words, but these things are cool. Why are they cool? They're really sensitive. I'll just show you results. We're working with a nanowatt or 2 of light. They're approaching film-like sensitivity, if you know silver halide films. Why? Same reason. One photon comes in, and might cause 10,000 monomer units to join up, just like in silver halide, you get the chemical application. That's important if you want to talk to industry, if you want to do data storage, if you want to do lithography, things that have to happen fast to stay cheap. Can get large thickness, and as an optical person, I like being able to have a lot of material out there to use. The resolution, people debate this in terms of how to measure it, but if you've done a good job with your polymer, it's certainly down to 20, 30 nanometers, and probably as much as 5. It depends a little bit on the polymer chain. I'll show you a little bit later that you can, even with cheap caustic substrates that themselves aren't flat, you can still make incredibly flat samples out of the materials, kind of magic. And if you're a little bit careful in the chemistry, they're low scatter, they're low absorption, they're just all the good things you want, even though they're not these beautifully grown crystals that you might be used to if you know photorefractives. Really easy to handle. You just cast them between glass slides, only dry processing. Notice I never said the word solvent or etch or any word like that anywhere along the lines. You pour the stuff in, it solidifies up, you write to it, you cure it with light, and you're done. That is really nice for certain applications, which I'll show you, where you really don't want solvents running around. And it's actually impossible to imagine you could get solvent down in the middle of that centimeter cube thing. You just couldn't get stuff there, right? So it's got to be direct processing. You can get pretty high index change. It's really easy, especially if you work with some smart chemists, to do all sorts of changes to the material. That's what I'll be talking about later on. And as an engineer, that's probably the most important word right there, is to just dirt cheap materials. And that gives you some cool applications. To do that kind of work, though, you better be able to measure what you did. I'll show you just scatter some results through here. I talked about the OFD, the optical frequency domain reflectometry. I'll talk about coherent reflectometry. We've done optical diffraction tomography. You need to be able to see what you're doing, because otherwise you're in the dark. Lots of good physics, and that is either scary or means you have lots of tools. You can go play with, make things do what you want. Here's the adjectives: coupled, non-local, non-linear, partial differential gradients. And they're stiff as well, if you know that word, which means unfriendly. But you can pull those equations apart, and we'll use that to design material responses to make them do cool things.